Good morning. Today we are going to see about hydration of cement. When cement reacts with water, it generates heat. It is an exothermic reaction. Why it generates heat? What's the reason when cement reacts with water produces heat? We can understand that in the manufacturing process, we have heated up the minerals, and after cooling it rapidly, we are getting a clinkers, and after grinding the clinkers, we are getting the final end product cement. So, when they are being heated up, some chemical energy is trapped in it, and that is the reason why it generates heat when it's being reacted with water. Heat of hydration. So we have seen that it generates heat, that is during when it is being reacted with water. So what are the final end compounds that we are getting in the cement manufacturing process? We have already seen that as C3S, C2S, C3A and C4AF. So this heat of hydration is nothing but the individual compounds, how much heat it will liberate when it's being reacted with water. That is called as heat of hydration of individual mineral compounds. Let us see the heat of hydration of individual compounds when it's being reacted with water. This is heat of hydration in terms of joules per gram. C3S 502 joules per gram, C2S 260, C3A 867, C4AF 419. This is the heat of hydration, that is, this amount of heat is liberated from each of these individual compounds when it is being reacted with water. And if you see here, the major heat of hydration is being liberated by the compound namely C3A, tricalcium aluminate. That is, it has a great affinity towards water when it is being reacted with water. This compound, what it means is, why this much amount of heat, what it means is, it has a great affinity towards water. That is, when water is being added to the cement, this will be the first compound to be reacted with water, and that is the reason why it is having greater heat of hydration when compared to other compounds. Now let us see the hydration of each and individual compounds, that is C3S, C2S, C3A and C4AF. Before going into that, I would like to recall that during the oxide composition, that whatever I listed as CaO, SiO2, Al2O3, Fe2O3, MgO, alkalis, SO3, these are the compounds, these are the elements which I listed during the oxide composition of OPC. There, for our simplicity, we can write CaO as in an abbreviated form as C, SiO2 as S, Al2O3 as A, Fe2O3 as F. Like this we can write. And also at the end of the manufacturing process, I have shown you a flow chart stating that how cement is being manufactured, and after that what are the stages it will be gone through. Right from the element stage, free element stage, next oxide state, then the compound composition, that is the formation of C3S, C2S, C3A, C4AF. Next stage is the hydration process, and in that hydration process only we will be getting the end product as CSH and CaOH twice. CSH gel and calcium hydroxide is the end product of any cement hydration. And in that I have told you, by varying this compound composition, we will be getting different types of cement. It is the flow chart which I shown you in the previous lecture. Now let us see how these individual compounds react with water to form the CSH gel and calcium hydroxide. First is hydration of C3S, that is hydration of tricalcium silicate. When this compound reacts with water, how it reacts and what is the end product, like that we will be going to see now. 2C3S plus 6H gives C3S2H3 plus, this is nothing but CSH and this is calcium hydroxide. The reason why I have written the mineral oxides in abbreviated form is for a simplicity, that is during the hydration process it will be much easier to denote it in a simple manner. For that reason we have written the oxide composition as just in an abbreviated form. So during the hydration of C3S, the end product is CSH and CaOH is nothing but the CH is being the CaOH is being abbreviated as CH. So the final end product is CSH and CaOH twice. Next, about hydration of C2S. In hydration of C2S, again the end product is CSH and calcium hydroxide. This is the hydration reaction of C2S. Next, hydration of C3A. C3A plus this is the hydration of C3A and this is nothing but gypsum, and when C3A reacts with gypsum in presence of water, it forms an element called as ettringite, and this ettringite is not a stable compound. Again in presence of C3A, it reacts and forms CSH and CaOH twice. Next, hydration of C4AF. And this is the hydration reaction of C4AF. And now we have seen that how each and individual compounds react with water to form a CSH gel and CaOH twice. Okay, now let's discuss why this hydration reaction is being proceeded like this. What's the reason why the water, when cement is being reacted with water, what's the reason for producing these hydrates, that is nothing but a CSH and calcium hydroxide? There should be any reason that for the formation of these compounds. Now let's see what's the reason for the formation of that compounds. The common feature in all cement minerals is that all the cement minerals have large anions and small sized cations. And what's the role of this anion and cation, and this is and why this makes a reason for the cement being attracted towards water, we'll be discussing now. As we said, large anions, small cations. When we see our final end product, that is the composition in a cement, what are those end products in a cement? That is called as Box compound, nothing but C3S, C2S, C4AF, C3A. Here if you see this, what I told you, in all cement minerals a common feature is that we will be having large anion and small size cation. So this is our end product in a cement manufacturing process, that is small cations, and this is large sized anions. Small sized cations bonded with large sized anions. So this is the composition which we get at the end of the cement manufacturing process, and that we get in terms of clinker, and after grinding it we will be adding gypsum and it will be ready for the process. Okay. This cation and anion are being bonded, and what we are doing is we are heating up the minerals to a high temperature and we are cooling it rapidly so that some chemical energy is trapped into it. We have seen it already. Now when this cation and anions are being bonded together, there is some space left between them, which makes them as an unstable compounds. That is, the packing density is lower, and that's the reason why these compounds readily react with water to form hydrates, that is water of crystallization. That is, to get a packing density, these compounds are readily reacting with water. That is, the small sized cations and large sized, let us assume that this is the cation and these are the anions. To fill up these spaces, and to get the packing density, it is being gets readily reacted with water, and that's how it achieves its crystallization. That is called as why we are telling that as hydration, that is products of hydrates. Hydrates are being formed during that reaction. So fill up these spaces, and to achieve this packing density, it is readily being reacted with water. So once again, we are having all cement minerals have a large anion and small cations. This is a general common feature in all cement minerals, and that's the reason why this cement minerals get readily reacted with water. That is why we are telling that as hydration. It is nothing but the products of hydrates are being formed when it reacts with water. That is called as water of crystallization or products of hydrates. So this is a cation and anion, and the space between them is being filled up with water to achieve the packing density, and that's how all these compounds are being reacted with water to form products of hydrates, CSH, CaOH twice. These are called the products of hydrates, and this is how the small size cation is being artificially enlarged to large size cation by incorporating the water of crystallization. That is, this when reacted with water, it takes the water of crystallization and it gets artificially enhanced to a larger size to achieve this packing density of order. This 0.64 to 0.74 is the packing density for a stable cement compound. To achieve this packing density, these compounds gets readily reacted with water. And here we have seen about the each and individual hydration of the compound minerals. Okay. And before that I have told you this C3A has a greater affinity to get reacted with water, that is it gets first reacted with water since its heat of hydration is higher when compared to other minerals. And now we can see in which order these compound minerals gets reacted with water. So when based on that heat of hydration, we know that C3A gets first reacted with water. Okay. If it happens so, then it does not allow the other compounds, that is C2S and C3S and C4AF. If it happens so, then it does not allow the other compounds to get reacted with water, and we will not be able to get the end product CSH and CaOH twice. Why it's so? And that's the reason why we are adding gypsum during a manufacturing process, that is at the end after grinding the clinkers we will be adding some amount of gypsum. Why we are adding the gypsum is to retard the reaction of C3A, since it has a much greater heat of hydration compared to other elements. To slow that process we are adding gypsum. This gypsum retards its affinity towards water, so that the other compounds can get reacted first. That is, the first compound in that way, the first compound to be reacted with water is C3S, next comes the C2S, C3A, and after C3A, and after that C4AF. In that order it gets reacted with water. And why it should be such? For that, while writing this hydration of C3A, I have told that C3A in presence of gypsum and water will form a compound called ettringite, and this is not a stable compound. Again it reacts with a C3A and only forms CSH, like that I have told you. If this gypsum is not added to the cement, then what happens is this C3A gets readily reacted with water. So this gypsum controls that action, and if this gypsum when added in a high quantity, when gypsum is added in a high quantity, it leads to false set. When gypsum is added in high quantity, then it leads to a false set. If gypsum is not added, then it leads to a flash set. So while adding gypsum to the cement, we should be careful that whether it is being added in a prescribed quantity. If it not so, then it will lead to false set. If gypsum is not added at all, then it leads to a flash set. That is, it won't when it is added in a high quantity, the gypsum itself will react with water and form a stable compound. That means the other compounds will not be able to react with water. Gypsum itself will react with water and form the end compound, a stable compound. And even if it is not added, then C3A readily reacts with water because of its greater heat of hydration, and it does not allow the other compounds to react with water. So I just tell you once again that the cement minerals generally have large anions and small sized cations, and they are in an unstable form. So it gets readily reacted with water to form a stable compounds, that is by reacting with water it will be forming products of hydrates using the water of crystallization. So to achieve the packing density, this cation, small size cation, is artificially enlarged so that it has been to a stable compound, and in the hydration order what happens is this C3A having a higher heat of hydration readily reacts with water, but it should not be such that, since it does not allow other compounds to react with water. So to control that, gypsum is being added. Even the gypsum should be in a prescribed range. If it not so, then it leads to a either false set or flash set. So after adding the gypsum in a prescribed quantity, what it happens is, first C3S reacts with water, then comes the C2S, C3A and C4AF. This is the hydration process. This is the order in which the hydration process takes place. So hydration is nothing but, since we are heating the compounds to a higher temperature, some chemical energy will be trapped into it. So to release that chemical energy, these compounds get readily reacted with water, and also those compounds are in an unstable state, and to achieve the state of stability it gets readily reacted with water. So in all the hydration reaction, what we are getting, the end product is as CSH and CaOH twice. So what's the CSH? The CSH is nothing a gelatinous gel-like member which is responsible for bonding action between the aggregates, sand, mortar. For that, the binding between each and individual compounds is because of the action of this CSH gel, that is the gel which is responsible for bonding. That CSH is a gel-like member and it is responsible for bonding. How this hydration reaction proceeds? Okay, we are having a cement grain, assume it is to be a cement grain. When a cement grain and it has compounds like C3S, C2S, C4AF, C3A. Since it is not possible for us to identify each and individual members through conventional techniques, we are assuming by seeing the cement grains, we are not able to tell the each and individual element composition. Assume this as a cement grain, and when it is being reacted with water, the products of hydration, that is the CSH and CaOH twice, are formed on the surface of the cement grain, or formed on the surface of the cement grain, and the hydration reaction proceeds from the outer of the cement grain. That is, first when cement and water gets reacted, the end products are formed on the outer surface of the cement grain. Then how come the inner grain of the cement gets reacted? When these products of hydrates are being formed, then there arises a pressure difference between the unreacted cement particle and the products of hydration. An osmotic pressure difference gets created and it acts as a semi-permeable membrane, and the products of hydrates will act as a semi-permeable membrane, and because of that pressure difference, this water will reach the inner grain of unhydrated cement, and this is how a hydration reaction proceeds. And how it's being done? Specific gravity of cement is 3.15 and specific gravity of water is 1. When these two get reacted, the products specific gravity will be somewhere in the range below 3.15 and above 2, and that's the reason why the products of hydrates are being formed on the surface of the cement grain. And after the products are being formed on the cement grain, there arises a pressure difference between these products of cement hydration and the unhydrated portion, and that membrane, the products of hydrates act as a semi-permeable membrane, and it allows the water to penetrate through it, and again the unhydrated portion gets hydrated. This is how a hydration reaction will proceed. Now I will show you how it happens step by step. Now we are going to see about CSH and CaOH twice properties. CSH, even in when C3S reacts with water, the end product is CSH. C2S reacts with water, the end product is CSH. Okay, which then makes a higher amount of CSH, that is the gel which is responsible for bonding. This CSH makes about 50 to 60% of the volume in an hydrated cement paste, and that's the reason it is responsible for bonding. C3S produces a lesser quantity of CSH and more quantity of CaOH twice when compared with C2S. C3S is responsible for early strength of concrete and C2S is responsible for later strength of concrete, and the CaOH twice constitute about 20 to 25% of volume in a hydrated cement paste. Now let's see about these volume proportions, in which order they'll be in a totally hydrated cement paste. Hardened cement paste, ettringite, 15 to 20%, CSH 50% to 60%, CaOH twice 20 to 25%, and remaining voids will be in the range 5 to 6%. In a hydrated cement paste, this is the volume range each and individual compounds will occupy. Ettringite will be in the range of 15% to 20%, CSH 50% to 60%, CaOH twice 20 to 25, and remaining air voids will be in the range 5 to 6%. Now, how the bonding action in CSH is responsible for the binding of elements. We are going to see that. How this bonding action occurs in CSH. The CSH has a large specific surface area, and that is responsible for the bonding action of CSH. And the main reason of bonding action is due to the intermolecular forces, or simply van der Waals force, are responsible for bonding of this CSH gel. The gel structures will be in the form of thin sheets. The gel structures will be in the form of thin sheets of 50 to 100 nanometer thick, and I will show you how the CSH sheets will be. And this is about what we are seeing is for CSH gel. Next, and another compound which is formed during the product of hydration is calcium hydroxide, that is CH. This CH will be in the form of hexagonal prisms, will not have a much greater specific surface area compared to CSH. This does not involve in any reaction after the formation of this compound, but it is responsible for keeping the pore solution in an alkaline form. The CaOH twice is a precipitate and it does not interrupt in any of the hydration reaction, and this is mainly responsible for keeping the pore solution in an alkaline form. Now I will show you how the CH will be in a hardened cement paste, how its a morphological structure will be in a hardened cement paste. Now I will show you the heat evaluation and hydration process graph, how this heat evaluation and hydration are being related. The graph is between rate of heat evaluation and time hours in x-axis. First in stage 1, that is, as I told you, that C3A has a higher affinity towards water, it gets reacted with water, but due to the presence of gypsum, it just retards its reaction and it forms ettringite, and that formation of ettringite lowers the temperature, and that is the stage 2. And after that, after the formation of ettringite, the C3S and C2S gets reacted in stage 4, and after the finishing of C3S and C2S hydration, the C3A, it gets reacted and the total hydration reaction takes place. This is how the hydration and the heat evaluation graph is being formed. This is a structure of a hydrated cement paste, total entire structure of a hydrated cement paste. Next we are going to see about the physical properties of cement. The physical properties of cement are what this fineness represents. This fineness represents the particle size of cement. This fineness plays a major role in the strength aspects of cement, that is the particle size of cement, and that's the reason why this fineness is to be tested in a cement particle. For this fineness test, a small cement particle gets easily reacted with water, whereas a large cement particle does not get easily reacted with water, that is the time taken will be more, and how it affects the size of a particle, how it affects the rate of development of strength, that is related to this fineness. How we can test the particle size of cement particle, and that's being discussed in this fineness. The size of cement particle plays a major role in the hydration process, since a smaller particle gets easily reacted with water, and also it affects the strength development in the later stages. And how this fineness is being tested in a cement is being done by 2 experiments. First is a field experiment. Field experiment is by sieving the cement particles in a 90 micron sieve, and after sieving, the particle left out on the sieve is weighed, and if it is less than 10%, then the cement is said to be okay. That is, it should not be greater than 10% for an ordinary Portland cement. That is, all the cement grains are in a more or less fineness. It can be done in 2 ways. One is by sieving and other is by using a Blaine's air permeability apparatus. Through sieving, we are taking a 90 micron sieve, and after sieving it for 10 minutes, the particle left on the sieve is weighed, and if it is less than 10%, then it is okay for an ordinary Portland cement. Next, by using Blaine's air permeability apparatus, here we are expressing the fineness of the cement through specific surface area per kg, what meter square per kg will be, the cement particles will be expressed in terms of meter square per kg. That is, after the cement being placed in a porous media, the air is allowed to pass through it, and how much time it takes for the air to pass through the cement particles is being noted, and that denotes the cement specific area. And for this OPC, the Blaine's fineness should be in the range of 300 to 500 meter square per kilogram. And now I am showing you the Blaine's air permeability apparatus. and this is where the test is conducted. In the top portion, the cement is being packed in a porous plate and it is being kept, and after passing the air through it, the difference in manometric fluid is being noted, the time is being noted, and that gives you the Blaine's fineness of the cement which we are testing, and it can be and it is expressed in terms of meter square per kilogram. Next, about the setting time test. Setting time, before proceeding this setting time, strength, soundness and heat of hydration test, we should be knowing about the consistency. Consistency is nothing but minimum amount of water required for a cement to proceed a hydration reaction. Minimum amount of water required for a hydration reaction to take place, that is called as consistency. First, we have to find the consistency of the cement which we are using, and from that consistency percentage we have to test the other tests, that are setting time, strength, hydration, soundness test and all. So, for calculating this consistency test, we have an apparatus called Bicket apparatus, and in that Bicket apparatus you will be having 3 needles which I will show you. And this is the Bicket apparatus, and these are the 3 needles. Starting from the top, it is the plunger, and next one is a needle which is required for initial setting test, and last is for the final setting test. And this consistency, that is the minimum amount of water, is being tested using the plunger. First, we have to take a certain quantity of cement and mix it with about 24% of water, and after doing it, we have to place that in a mold. After placing it in a mold, we have to allow this plunger to penetrate into it, and we have to note the reading, that is from the bottom 5 to 7 mm. When it reaches a position of 5 to 7 mm, when the plunger shows a reading of 5 to 7 mm, that is said to be a that is when this plunger reaches a reading value of 5 to 7 mm, that range is said to be a consistency limit. That is a minimum amount of water is being added to the cement. We have to note the water content. Like this, we have to repeat till we are getting 5 to 7 mm. After getting that 5 to 7 mm, we can note the corresponding water content. So, on that water content will be the minimum amount of water required for a hydration reaction to take place in a cement. Setting test, setting time test. The setting, what is it is, that is the change of state from fluid to solid state. When the cement changes its property from fluid state to solid state, that time we are noting. When it changes its state property from fluid to solid, that is called as setting time. In that we are having 2 initial and final setting time, and as I already show you in that figure, I have told you the needle for initial, which is the needle to be used for initial set time and which is the needle to be used for final set time in that Bicket apparatus. So, in the initial set time, after noting the consistency of water, we are taking a certain quantity of cement and mixing it with the percentage of water what we got in the consistency, and we are placing it in the mold, and by replacing the plunger by the initial set needle, we are allowing the needle to penetrate through the mold, and now we are noting the time elapsed between the initial mix of water to the cement and the time when the needle reaches the 5 to 7 mm, and as specified by our IS standards, it should not be more than 30 minutes. That is, the elapsed period should be within 30 minutes, right from adding water to the penetration of this needle to 5 to 7 mm. This range is called as the initial set, and as per our IS standards, it's being recommended that it should be within 30 minutes for OPC, ordinary Portland cement. And for a final setting time, what we are doing is taking a certain quantity of cement, again mixing it with the standard water percentage what we got in standard consistency, and again filling the mold. This time we are replacing the needle by the final set needle, and again we are noting the time right from the adding of water to which the needle fails to make an impression. There will be a circular edge, and in the center will be having a needle like structure. We will be noting the time difference till when the circular edge fails to make an impression in the mold. That is where the cement has hardened. That is the stage where the cement has hardened, and that's the reason why the circular edge fails to make an impression in the cement paste, and that denotes from that stage the cement is entering into the hardened stage. The initial test is being done to determine the setting time, that is when it start losing its fluid property and entering into a plastic stage, and in the final setting time we are about to know when it is entering into the hardening stage. Next is the strength test, which is nothing but the compressive strength test. By doing the compressive strength test, we are determining the strength of cement. That is I have already told you that OPC grade 53, 43, 53. I have already told you that OPC will be available in the range of grade 33, 43 and 53. Based on this, we will be getting the corresponding strength. Strength test is nothing but the compressive strength of the mortar. We are finding out the strength of the cement, whether it belongs to OPC grade 33, 43 or 53. For that, again we are doing test based on the consistency value what we got in standard consistency. P/4 plus 3% of combined weight of cement and sand, and we are mixing it with water, and after that we are placing it in a mortar mold, and after a curing period we are testing it by placing it in a compression testing machine, and from that we are able to get the strength of the cement used in the test. This is the compressive strength test. Next, soundness test. This soundness test is mainly done to determine whether a cement will undergo any volume change when it is being used in the hydration process. Any volume changes, if it's so, then that cement will cause a serious effects in the durability property of the structures. So to avoid it, the soundness test is done. Again, the soundness test is done by Lee-Chatterless apparatus. There we will be placing the cement in. There we will be placing the cement in a mold, which I am showing you, and we will be noting the reading between the two needles, and after heating it and cooling it for 24 hours, again we will be reading the reading between the two indicators, needle indicators. If it is supposed to be greater than 10 mm, then that cement is set to undergo shrinkage, that is volume changes. If it is less than 10 mm, then it is said to be a sound cement. If not so, then it is said to be an unsound cement. And what causes this volume changes is mainly the excess lime. The excess lime, if any excess lime is present during the manufacturing process, then that is responsible for this volume changes. That lime again gets reacted with water during the hydration process, and it produces some volume changes. So to find out that, we are doing this soundness test. Heat of hydration test is meant mainly for low heat cement. While this the heat of hydration for low heat cement should be in the range of 65 calories per gram at 7 days and 75 calories per gram at 28 days. This is the range in which the heat should be evolved at 7 and 28 days, and for that purpose mainly we are using this heat of hydration test. And next is chemical composition test. This I have already told you as a control ratio, that is lime saturation factor, silica ratio and alumina ratio. The prescribed ranges, whether or cement is within the prescribed ranges for a lime saturation factor, alumina factor, silica factor, that is this chemical composition test. And that's all about the physical properties of cement.